Hello and welcome back to Calculus 2. This is going to be a very short lecture because it is a very short lecture. 8.6 alternating series. So this is a procedure more than a theorem, and I like to present it as a tree, you know, the diagram. So this is what's happening here. You recognize alternating series when you see the alternating term followed by some kind of an from whatever to whatever, right? To infinity, obviously. Now, this 1 over negative 1 to the n can also be found as the cosine of n pi or sine of n pi over 2. So these are the three different things that will trigger alternation. What is the meaning of the alternating? When you have alternating sequence, you get numbers that jump on the opposite side. And then when you add these to infinity, they might add to a finite value, or they might add to infinite, which is, again, divergent. So how do we deal? What is the procedure? The first thing you do is you free up, so you're looking at minus 1 to the n an, and you free up an. You take the an term in consideration first, and it has to fulfill two conditions. An needs to be decreasing, and the limit needs to be 0. You are going to have a yes branch and a no branch. If these two conditions, I'm going to label them condition 1 and condition 2, if these two conditions are satisfied, you are moving down the yes branch, which is a convergence branch now, and you are going to have to look at the summation of just an. Observe that there is no alternating term there. And now that one can converge or diverge. If it converges, we have something that is called absolute convergence. And if it is divergent, we are going into conditional convergence. If it's a no, then use something else, because it could still converge by using different method. So most of the time it diverges if it's a no, most of the time. But there are these cases, these specially carefully crafted problems that could still converge by having a no on one of the two conditions. So you have to be a little bit careful about that. So this is your procedure. Now let's test this out on the problem. It is much more systematic to see it in a problem than to do this. I'm going to look at alternating harmonic series. What do we know about harmonic series? Diverges. Harmonic series, 1 over n, divergence. But alternating, let's see what that does. Alternating harmonic series, summation 1 to infinity, negative 1 to the n over n. This is alternating harmonic series. So where do we begin? we understand that an is just 1 over n. That's what we know. We need to take the limit of 1 over n as n goes to infinity. We get 0. And we also know that it's decreasing because the graph or derivative, whatever you like. So you see that both conditions are satisfied. We are going down the convergence branch, and now I need to check what's happening with just an, series of an. Now, what do we know about this? That diverges, which means that we are ending up with a conditional convergence. Now, sometimes in mathematics, if you pay attention to the language and words that are used to describe a certain concept, the whole thing makes just so much more sense. We said that we are going on to a convergence branch. That means that the main problem must already converge. But then that convergence is broken into two categories: absolute convergence and conditional convergence, which is further fueled by whether this partial problem converges or diverges. Now, this is a perfect example to understand conditional convergence, because the word conditional, right? Condition. There is a condition for it to converge. Look, if you have a problem without alternation, it diverges. If you have a problem with alternation, it converges conditionally. So what is the condition for it to converge? For alternating piece to be in, right? It's because of that it converges. It converges under the condition that that thing is present, because if it's not present, it diverges. You see that? It's a really good language use in definition. So the pathway will always be like this. You get a problem. Problem contains alternating piece. You strip away alternating piece to just get the sequence. You test the sequence against two conditions. If both conditions pass, you are going down the convergence branch. In the convergence branch, you will solve the series using any of the 9 tests that fit to solve that problem there. Could be ratio, could be root test, could be integral test. Hopefully not integral, right? And then, because in that case, insert page here, right?
How can you tell if it's going to be divergent? Because I know you hadn't taken the antiderivative of, it's going to be like -1 divided by n squared to the infinity and 1, but how are you going to identify?
You mean, how is this divergent?
Yeah.
We know that because we proved it when we did the integral test. We proved that the harmonic series is divergent series. So from this point on, we just memorize that because it's used all the time. We're using it here. We used it in a previous section to show comparisons. So all of you, do yourself a favor and memorize that 1 over n is called harmonic series and it's divergent. That's it. So this is also a perfect time for me to discuss the following creature. 1 over n is the sequence. It's convergent. Summation 1 over n is a series. It's divergent. -1 over n, sum of that, is alternating series. It's conditionally convergent. And here is something in this section where you really have to pay attention on the language, the exact problem, and what actually happens. Because do we see 1 over n in every single one of these?
No.
And we see
Yes.
all different things over there different, right? So sequence converged, series diverged, and then alternating series converged conditional, right? So you have to be very, very careful. What is sequence? What is series? How many tests do we have for sequences? How many tests do we have for sequences? We have only one test for sequence, which is you take the limit, it converges or diverges. That's it. Maybe you want to add that to this sheet on top. The only test for sequences is the limit n goes to infinity. Because that is it for sequences. Sequence has the an sequence, right, with commas. It's a list, order list of numbers. And the only test you have is limit of an. That's it for sequences. Series is this chart of 10 different tests.
I think there's actually two.
No, we only have one.
No, I meant like we have the limit as n goes to infinity b of n equals L.
No, those are the conclusions of it. But we only have one test, and the conclusions is convergent or divergent. All right, guys, we have time for another example. As I said before, this is highly structured. So here's a good one. Actually, no, this one is solved in a book. Let me find so 16, because we already solved this problem to some extent. 0 to infinity, negative 1 to the k squared plus 10. You remember this problem?
Yeah.
It was convergent, right? By comparison test. Where do we start? We start by stripping ak, which is 1 over k squared plus 10. So all we do is we remove the alternating term, which is in this case negative 1 to the k. We remove that and we got ak. So now limit k goes to infinity of 1 over k squared plus 10 is 0. Pass. And we know it's decreasing because it's 1 over x squared. We know how 1 over x squared looks like, right? And this is plus 10, so shifted to the left 10 units. So it is decreasing.
Actually, you have to shift. You have it shift up 10.
No up 10, left. It's goes to negative 10 like that.
No, I mean like what's in the square root, what's in parentheses is when you shift it left or right, and what's in plus 10, you have to shift it.
No, a plus 10 would be here, on the after the fraction. Oh yeah, you're right. If it's plus, yeah, but it's gonna work like this. It's gonna be some kind of shift like that because you don't have a. If it's like this, then you go 10 up.
Yep.
If it's like this, you go 10 to the right. Now, if it's like this, you're still going left and right, but it's a different value because of the square. You will have to do. But the point is it's still decreasing. It's still decreasing because it has the form of 1 over x squared. As long as it has a form of 1 over x squared, we're good. Both conditions hold. We are going down the convergence branch. I need to check what's happening with the summation 1 over k squared plus 10. Now, we already did this problem, right? Did this problem before. use direct comparison, it converged. So we have the convergence there, therefore convergence plus convergence is absolute convergence. So this problem is absolute convergent. One more, and then leave.
I may ask you a quick question. So do you take like the decay of it? Is the direct comparison when you take the decay of it?
Yep, so you actually have to insert here the entire problem that we did here. Where is the problem? See this problem?
Okay. Yeah.
So we have to put all of this work that you now see on the screen, all of this work has to be there. So when I do alternating test, I technically test two tests, right? Because you will always have another test midway, right? So all of this needs to be inserted right here, where I put this. All of that page or half a page work needs to be done there, and then you're claiming convergence on. The reason why I didn't do it is because we just did it 30 minutes ago. So the last problem for tonight is the 26 summation from 1 to infinity of -1 to the k plus 1 d k factorial k to the k. So I'll let you work a little bit on it for about an hour, and then I'll jump in.
That we can do it.
Mm.
With this, put no way to noise really well. So I'm doing I'm doing a k equals k factorial k with k, you got angular affinity. I think it's equal to 0 pretty much. It's decreasing. Can't be.
You have to show them.
We can't show it because we never in our entire lives have we did factorial graphing.
Then you have to do proof by showing that the next term is smaller than the previous. There are three ways to show decreasing.
I know divergent test, no, can't use that one, but I know
It's not a
I'm trying to
it's a proof. Three different ways to prove decreasing. It has nothing to do with this course. All of them are before this course.
but separating them out, but can't do that part. I thought nobody can print all this stuff.
You guys done? So why party?
Because
Scout 2. Scout 2, it's blood, sweat, and tears. I don't want to hear any laughter. There's no laughter in this class. So how do you show decreasing, guys? What are the three ways to prove that something is decreasing? What are the three different ways?
do a of k is equal to k factorial divided by k over k.
What are the answer is not in Calc 2. The answer is before Calc 2. No. Derivative is one of them, so we can't take derivative because of the factorial. So that goes out the window, but that's one way to show that function is decreasing. Take the derivative. What are the other two methods to show that something is decreasing? Graphing. Can't graph because k factorial. What is the third, last resort, which is one we have to use here to show that the function is decreasing?
ln.
Nope. It's the definition of what decreasing means. And that is that the next term is smaller than the previous. You need to show, and that's the one you have to use. You need to show that an plus 1 is smaller than an. That's the definition for decreasing. The next term is smaller. This is the next term is smaller. So you actually have to, you are going to show, limit of this equals 0 is nothing, right? The fastest growing function that we have in the galaxy is in denominator, right? So we're cool there. We know it's 0. So that condition is done. This is the one where you actually have to crank a little bit of work to show that the next term is always smaller than the previous, and then you have your decreasing part. If both of those conditions hold, you are on a convergence branch, you get to do the ratio test, right? So we strip away AK. We go with the limit k factorial over k to the k. K goes to infinity equals 0 because boss is in the denominator. Check. And then I need to show that k plus 1 factorial over k plus 1 raised to the k plus 1 is smaller than k factorial over k to the k. I need to show that. So what do? Cross multiply, cross multiply, and then peel off and do some stuff, right? Well, what I'm going to do is I'm going to actually just take this term and bring it here, and take this term and bring it up there, right? So I'm going to swap the terms. So I will have k plus 1 factorial over k factorial to be smaller than k plus 1 to the k plus 1 over k to the k. K plus 1 on the left peels off, leaving k factorial behind over k factorial, and they die. On the other...
We will get to 2k factorials with
what?
each other. And is that
You
possible?
You pull k factorial from here. K plus 1 term separate and k factorial stays behind. It's the next term. Then you have k plus 1 times k plus 1 to the k over k plus 1. Now, k is at least, you look at the problem, 1. Right? K starts at 1. So we can divide both sides by... Wait, hold on. This is supposed to be k to the k. There we go. So now what I have is k plus 1, and I'm asking myself if that's better or worse than this. Divide both sides by k plus 1. We get 1 less equal than k plus 1 to the k over k to the k, and this is where you can bring k to the k to the other side, and it's proved. So you just shovel this algebra left and right and left and right until you get the true statement. So the more you do this, right, the more practice you get, it's gonna get easier. Your test is next week, so you have the entire weekend, right? So we proved the decreasing part. We proved the limit. We are going down the convergence branch. We are supposed to look at k factorial over k to the k. We use the ratio test. In interest in time, I will tell you it converges because I'm divine, and we are getting absolute convergence at the end.
How can I identify if you're going to get absolute convergence or not? I mean, how can you?
Because I know, years of experience, I say do the work, and I'm telling you which test to use. So you have to, right, sit there, get AK plus 1 and stuff from the earlier today.
And you said we can only identify if it's constant conditional convergence if it's like -1 in k, whatever small.
Conditional convergence you get when this one over here when this step diverges.
Yes.
All right, we just saw it. Bye, stream.